Okay, let's begin. So we're going to be going through the EM algorithm for estimating a mixture. I'm going to do it in the context of a two-component mixture. You're going to do it in the context of a k-component mixture on the homework. I'm going to work out everything in a one-dimensional example, and you're going to do it in a higher dimensional example. So instead of one-dimensional Gaussians, you might use multi-dimensional Gaussians. Not a lot changes in that. So I'll show you the EM algorithm again. We'll go through it. You have some proof that it works. And there probably are some lingering questions about that proof. Even if you went through all the details, you could derive everything, do everything that I did, there might be some questions still. There's been zillions of papers written on this algorithm, the correct way to understand it. I think when it was originally written down, it was a little bit elusive what's going on here. That Q function is not cap F, which we're trying to optimize. But there's a certain brilliance to it. That instead of just maximizing cap F, after I integrate over the latent stuff, in one fell swoop, it shows you an iterative algorithm for doing it. And so it turns this optimization problem into this hill climbing algorithm, this iterative approach. And how you handle each iteration is a little bit up to you. But in a lot of problems, you'll probably do the typical thing, take derivatives, set them equal to 0, and solve. If you want to do something fancier, that's possible as well. I will say, for a Gaussian, something like that, the log likelihood is a parabola, okay, or a paraboloid. There are algorithms out there that can climb a paraboloid in the number of steps of its dimensionality. And so in a two-dimensional Gaussian, if you take the log likelihood, you can climb that in 2 steps. It's possible. You never have to traverse the same direction twice. So conjugate gradient algorithms will do that. We're not going to do anything quite that sophisticated, but if you want to learn lots about optimization algorithms, ISE teaches that. And so you can go take a lot of different optimization. What they're going to do is they're going to break it down into subclasses of different types of optimization, so you'll learn how to solve those. Lots to learn about that, if you want. Otherwise, you make a friend, and they're your research collaborator, and they do that part for you. I do that all the time. So sometimes I don't have time to do something, I kind of understand the gist of it, but I'm not an expert, and I go make a friend. That's what universities are for. So hopefully you take advantage of that through your research career. For this problem, you'll be able to do it all by yourself. So you don't need collaborators for this. I wrote down everything in terms of k-dimensional mixture. So we'll kind of go through that, and I'll say you can induct and do grad school induction. If it works for k is equal to 2, it must work for k is equal to k. So after a while, you gain some intuition about that. If you want to do it for k components, you can do it directly. You don't need to do an induction proof. But usually what I do is I usually do everything in the smallest dimensional example, work out the math, and then I induct in my head. I go, it's got to be this way. The EM algorithm, again, is this. So EM is just these 2 steps, but I'm going to iterate in a for loop. These steps. Iterate 1, I figure out this function Q theta, given theta, I'll say T, and that's equal to the expected value of the log of the complete likelihood function. So this is going to be over theta and psi. Maybe given my x's, I'm thinking about this in terms of a likelihood function. Before I wrote this down is little f. So my likelihood function in the context of this example will be my little f function. So some people call this the complete likelihood. I kind of just call it the likelihood. It's got all this stuff in there. And so, name of the game to most things in this class is write down the likelihood function. You get a process, I tell you how data is generated, you should get to a point where you can just write down the likelihood function to everything. That might take you a couple more classes to practice, get really into it. But in my career, writing down the likelihood is always step one to everything. So write down the likelihood, and it'll tell you a lot about where the parameters live. I wish we taught that all through undergrad statistics. Just write down likelihoods, try to figure out what they mean. Everything is derived through them. It's not quite true. We've seen method of moment operators, estimators, and they don't use the likelihood. I'm going to argue throughout this class that's a bad idea. So even though it could sometimes work out for you. Okay, so I figure out this where I'm integrating over psi and I'm conditioning on the previous data point. So that's where that conditioning comes from. We'll be explicit in the context of this example in a moment. And then I maximize. So I take the R max over theta, and I apply that to my Q function, theta t, and that's going to give me theta t plus 1. And so I'm going to iterate this thing through for loop. And I'm going to do that until this thing converges. That all of a sudden the thetas aren't changing very much on each step. So if all of a sudden they're changing at the 4th decimal place on each step, but they're not changing in the first 3, that means you're converging. And so you can stop once you get as many decimal points as you feel like reporting. You don't want them to fluctuate anymore. You need to check in this sort of thing that you're not in a local. And so if this is a multimodal problem, then you need to be careful. I don't mean multimodal in terms of the mixture. X is multimodal, we know that in a mixture model. This is an additive mixture model, but we need to think about multimodality in terms of the thetas. So what do? To check that, I'll give you the engineer's approach. You start at different locations, you run this thing, you make sure that it's converging to the same stuff. Let's say I run this 10 different times. 10 different starting points, all far separated from each other, and I get 3 different answers that it's converging to. How would I check to see which one is best? Yeah, you look at the likelihood. Go back, plug everything back into the likelihood, and look at which one is highest. So that's it. So usually I have that built into lots of my iterative codes. That it'll run it a whole bunch of different times, it'll converge to something, and then I do a check. If you run something like k-means, it also will do that in like MATLAB or R. It'll probably pick like 10 starting locations, something like that, and you usually have control over where you start from. You should always control all that stuff. So not just reside on the defaults. And so you want your code to converge quickly if you start from good locations. Maybe you have good locations, but your algorithm should also work if you start from rather terrible starting locations. So if it doesn't, then you're going to produce code for that poor sucker graduate student in a few years, and they're going to go, why doesn't this thing work? And there's no documentation on any of it. So basically the stuff people do to you. So you could clarify this for them. Okay, for the multi-dimensional, or the k-component mixture, somebody told me last week they like the answers. They want the answers up front, and then they want me to derive them afterwards. So I'll try it that way this time. So for the k-component mixture, these 3 steps right here are the solves to Q. So what we're going to be able to do is we're going to work out Q analytically, so I'm not actually going to need to reiterate that step, because I'll have it in closed form. There'll be nothing to do after I have it in closed form. I just keep using that same form, and then we maximize. And so what I've done is I've taken partial derivatives, set them equal to 0, and I've gotten these updates right here. I want to point out what these things are. What I'm going to get is I'm going to get a probability, so this probably should have an R right here to denote probability. It's a discrete thing. This is the probability that the xi point comes from component ck. Okay, so sometimes, well, I'll write it like that. I like that notation. So the xi point has come from that component. So we're going to get probabilities for all of those. So let me just draw a picture. Let's say I have a two-component mixture. I'll make that come down a little bit more. And let's say I have, so I'll call this component 1. So e.g. C1, and this is component 2. If I have this point xi right here, and keep in mind, it's some step during the algorithm, I know what the mu's are. So this is going to be based off of whatever my approximation to the mu's and the sigmas are. Let's say I had those. If I knew what mu1 was in mu2, keep in mind we'll have to converge to these answers as well, and I knew what the sigmas were, sigma 2 and sigma 1. What do you think the probability that this point right here came from component 1 is? Just make a guess. Yeah, it's close to 1, right? So we're on the left-hand side of mu1, this standard deviation, can't get it over here, probably. It's hard to say. There's a little bit of, 2 SDs out, 1, 2, probably not. So it's probably well under 95%, or well over 95% that this came from component 1. So we're going to be able to compute that probability, and those probabilities for each data point are going to be important. We're going to compute them, and I'm going to show you how to compute them, what that formula is. It's going to be an application of Bayes' theorem. Once I have those probabilities, the mu's are going to come in this form right here. And so I'm taking in those probabilities right here, and then I'm just computing this. This is a weighted average. That's all this is. So these are my probabilities times my xi's, and I'm dividing by my weights. That's called a weighted average. So if I knew exactly which components everything came from, and there was no uncertainty, if I gave you the labels, then these probabilities would be 1s and 0s. So I would know exactly which one came from what. So what would this be right here? This would be 1 when it came from component 1 and 0 otherwise. And so I'd have all these 1s, so it would just be a sum over the xi's that came from component 1. And then I would be dividing by this, but this is a sum of 1s and 0s. And this would sum up to the number of x's that came from component 1. So this looks a lot like x bar to you, but it's averaging over uncertainty. The answer makes sense. So I like that answer. For the sigma matrix, so I've written this down in k dimensions. So keep in mind xi, if this is high dimensional, let's say it's like 3-dimensional, xi's would be 3-dimensional. The weights are 1-dimensional. So I'm just summing over vectors. Similarly, for the covariance estimation, I'm taking an outer product right here. So this is a matrix. So this is a vector going this way, and this is a vector going that way. That's an outer product. And same sort of thing, it's just a weighted average of that. So this looks a heck of a lot like the outer product divided by n for the number of things that came from component 1 if I knew precisely the component labels. And that's probably what you would use to estimate the covariance structure. You might have, if it's a d-dimensional analysis, some of you might divide by n minus d down there. That's the unbiased estimate. This is like the MLE. So the MLE for a univariate case is when you divide by n, not n minus 1. So I will make the argument a little bit later, and the book does this in chapter 7. That's a better estimator. So why do we teach the other one? Because it's unbiased. Why do we like that? Because we're fools. So it's true. So on average, it's farther away. It's a worse estimator. Does it really matter? Not too much. So why do we teach that? Because we don't want to explain to undergraduate students that biased estimators can be better. So why don't we like to explain that? Let's go back to my original reason. We're fools. So it's your job to correct that when you get in the classroom and start teaching undergraduates. That's no longer what we need to be teaching. I think. What do you think, Eric?
I think about all the times they told me you divide by n-1 because you estimate one parameter x bar, and now I can think of how silly that argument is.
Yeah, I mean, it's true. That is the degrees of freedom in everything. So that is a true reason, but it doesn't mean it's necessarily better because of that. It's like, does that mean it's better?
I actually got a really good question from an undergrad last semester when we were talking about covariance. It's like, there are two, like, x bars or whatever in your covariance, so like two averages, why do you not divide by n-2? And that's actually a really good question.
Yeah. So usually we come back and we report with the degrees of freedom answer. You can say from now on, well, it's unbiased and maybe you like that estimator. There's other things to consider. And then tell them about it. And then you tell them something like, but for the test, if I ask you for an unbiased estimator, this is the one you would report. And later on, I'll try to convince you there's other good estimators and you want to take another class. Maybe something like that, I'm not sure. So, see how that works, let me know. Okay, so we're going to walk through these steps and try to derive these things. This is your answer. This is what you're going to be coding up on your computer. I want to just point out, in terms of our notation, this right here is the probability that xi's come from component C1 in this case. And this right here is the probability that any xi's are going to come from component 2. Right there. I'll also just remind you, this thing right here, this is f of x given mu2, sigma 2. I can square it if you'd like. And it's going to be conditional on that C is equal to k, or 2. In my notation. So this is the conditional distribution. This is the probability of coming from C2. This is the probability of x coming from component C2. So these two things multiply together, the joint distribution of things came from C2 and you get the x. So this is a conditional distribution based off of the C when I multiply a marginal distribution into a conditional identity. So that's what that represents. So just keep that in mind, all of that notation. So again, I haven't really written down the C in here, but it's implied by these things right here. So this is the C. Okay. So let's see if we can derive all that. So this is pretty easy to code up. It's just these steps that you're iterating through. So all you're going to code up for your homework is inside a for loop, you'll compute these probabilities, then you'll compute the mu1, mu2, so you'll have these little sub for loops for the k's. In here, you'll update them for each one of the k's. And so they'll probably be 4 is, k goes from 1 to cap k. You'll need those. You don't actually need to compute all cap k of the probabilities because they're constrained to add up to 1. All you need to do is compute k minus 1 of them. Saying that if you do compute the kth one, it won't bog you down too much. This right here is not, I want to just point out, that pi is not these, but they're related to it. And so this is my probability of each xi coming from a particular component. If I wanted to estimate pi k, this is just a side question, because I didn't write it down. If I wanted this, how would you compute it? So I've got the probabilities that each of the xi's came from it, but this is that total probability that is in our model. They're not the same, but they're related to each other. What would you do with these if you're going to compute pi I k? Pi k, that's what I mean. Somebody gives you 10 numbers, 10 probabilities, all between 0 and 1. So here's for 10 different data points. I actually, now I want to know what the total probability is. What would you do with that? Some of them are big, some of them are small. Somebody runs into the office right now, says, I've got $1 million for you, I just need a reasonable answer. Average? Yeah, why not? That is the answer. Sum of the pi I ones divided by n. That actually is the MLE for this case. It's the average. I know I've told you before, don't always be thinking about averages, but they do pop up pretty regularly. So for this model, this is the right thing to do. So if I wanted this for the k component right here, I would substitute that with a k and substitute that for the k. And then I can compute all of them. So the maximum for these things is riding along in this algorithm. I don't compute them at every step, maybe. Maybe you do, maybe you don't. We'll look at that. There's a couple different possibilities of what you can do. Okay, let's get down to it. So I said the first step to everything is write down the likelihood. We'd started doing that. And I just need to do some simplifications. Also, this assignment that I put up, this is on the web page. It's going to be due April 22nd. So what I've said, and we can come back and look at that, is do a simulation study where you consider some different dimensions in different k's and show me when the algorithm works well and when it fails, when it doesn't work well. And so you can play around with that. Obviously, if I've got k components, but I only have, let's say k is 10, and I only have 6 data points, good luck with that. So you won't be able to estimate everything. You're going to have ridges all through that likelihood function. It's flat. So I'm going to need at least as many data points as I have parameters to do the estimation. If the modes are very close to each other, then the algorithm doesn't do very well. If I have just one mode in there and I try to fit a 2-component thing, it's never going to actually converge. Like the mu's won't converge, but some linear combination of them will converge. So it'll converge to something on a ridge as well. So you won't be able to estimate everything. And that makes sense. So you'll go through a few different examples, write it up, show me a graph or two, tell me how it works. It works pretty well. Okay. So the likelihood. And again, this is the complete likelihood because I'm going to have the c's buried into it. And again, I don't ever say complete likelihood, I say the likelihood. And then if there's some other likelihood that I'm dealing with where I've integrated something out, I tell people that. I've marginalized over this particular parameter. So I try not to make it too elusive. So the complete likelihood looks like this. I goes from 1 to n. I'll write this down using summation notation just to make my life a little bit easier. And just keep in mind what these things are right here. These are density functions. And so I'm going to have these f, well, I should just write it out like this. I'll write it down as pi 1 pi k over root 2 pi sigma k e to the minus 1/2 xi minus mu k squared over sigma k squared. But I need to be a little bit careful, and I need to include an indicator function. So if I just wrote this down, this right here really is just my fx I given theta. So I'm just producting over that thing, but how does fx come into play? It's these two things. But only one of these components was turned on at a time. So the x either came from here or came from here. It didn't come from the average of these two things. It came from one or the other. And so we need to be specific about that. So we'll include an indicator function that xi comes from component k. And I'll write it down like that. So this is just an indicator. xi from component k. So in this sum right here, so again, this is all in here. Only one of these is turned on at the right time. I need to know the labels to be able to do that. We're going to average over those labels because we don't know what they are. And that's what this step is going to be all about. So my missing variable psi is now the c's. It's the thing you don't get to see. Okay, so I'm going to do this just a little bit differently. I'm going to rewrite this. Oh, and if you don't mind, since I'm writing down a likelihood function, I'll write it down like this. Theta, given my x's, is that this is always defined just up to proportionality. And so I can get rid of that. It's just a constant. It's in everything. It's always floating there, so we can toss it. Likelihoods are self-relative. That doesn't have any of the parameters in there. I should probably also remind us what this notation is. That's my mu's, mu1, mu2, sigma 1, sigma 2, and pi 1 and pi 2. I don't really need both pi's because I know they sum to 1, they're probabilities, so they're positive. I should probably write that down. So let me just do that. Pi 1 plus pi 2 is equal to 1. That's a constraint we're going to have to obey. When you hear constraints, maybe you're thinking Lagrange multipliers. I'll say something about that once we derive this MLE. And pi 1 and pi 2, both of them are greater or equal to 0. I would say they're greater than 0. Otherwise, why are we plugging it in? So it'd be a pretty superfluous way of writing down your model if I had a whole bunch of 0 weights in there. So I'm going to say they're positive. Okay, so I'm going to just rewrite this whole thing. I'm going to get rid of the 2 pi. So we'll just forget about that. And I'm going to rewrite this function right in here is just e to the minus 1/2 xi minus mu k squared over sigma k squared. And then I'm going to throw a whole bunch of stuff into the exponent. So I'm going to deal with these, and I'm going to jam them into the exponents. This is going to be plus log pi k minus log sigma k. So that's all in the exponent right there. Keep in mind, there's just one term in here for every sum. So if this was cap k, only one of these would be turned on. So one of the indicators is a 1, and the rest are all zeros. I'm going to write this down slightly differently. Well, I'll just write it down like this. So I'm going to take this indicator, and I'm going to jam it into the exponent as well. It kind of slightly changes the way we're thinking about this mixture. But again, there's only one term in this big sum right here. There's not k terms. Most of them are zeros. I'm going to just change this into product form. You can convince yourself that this is exactly the same thing. I goes from 1 to n, haven't changed anything there, and I'm going to change this into a product. My cap k is 2. This looks like this. E to the minus 1/2 xi's minus mu k squared over sigma k squared plus log pi k minus log sigma k. And then I'm going to do something in here. Ci is equal to k. So I'm just going to change this. And I'm going to change this notation just a little bit. I could have written down Ci is equal to k. To me, they mean the same thing. So choose your notation. So the xi came from component k. Right here, that's one way of writing it down. But keep in mind, when we did all of this and we were flipping coins to decide which component we are in, there's actually this Ci that's running around. And so Ci is just the component label for the ith iteration. I kind of like writing it down that way a little bit better. So I can think about all of those CIs in particular. This right here, this component K, this can either be a 1 or a 2. This I right here, the way that I'm writing it down, and slightly changing the number, there's n of those. There's n CIs. For every xi, there's a CI. So I'll just write it down like that. Same exact thing. I mean that. So this is my 1 or 2. That's going to be now 1 or 2. And so what I've done is I've jammed that thing into the exponent. Let's just think about what this formula is right here. What this function, when that's a 0, it makes all of this a 0. E to the 0 is a 1. And so I'm producting now a whole bunch of things that are 1s. So imagine this was cap k. Cap k minus one of these would be 1s that I'd be producting up. And then one of them would have this exponential form. If I think about this in the additive form, cap k minus one of these is 0, and one of them has the exponential form. So they're exactly the same equations. So I've just kind of changed the way I use the indicator function. The reason I've done this and written it out this way is, well, it makes a clean solution, but we're going to be working with the log likelihood functions. So we're going to have the log likelihood, and I would like to make it look as easy as possible. So I know I can take both these products now, shove them up in the exponent in terms of sums, and the log likelihood is something that I can write down, and it's just this quadratic form. Okay. So this is just looks like this. E to the minus, I'll write it like this, sum, double sum, I goes from 1 to n. K goes from 1 to cap k, which is 2 in our example. This will look like this. Minus 1/2 xi minus mu k squared over sigma k squared plus log pi k minus log sigma k. And then I've got my indicator function. Ci is equal to k. Close that brace. So there's the likelihood. So let's take the log likelihood. So the log of my likelihood function. And I should probably write down the c's in here and denote that I have them. And so that's the notation I would typically use for that. Before I just wrote down the x's, but I did write down the c's over here. So I kind of like it. It makes me feel better when I include that in the notation. So I can remember that I have all that stuff. So let's just change the notation. Put the c in there. So this thing is just going to look like this double sum. I goes from 1 to n. K goes from 1 to 2. Minus 1/2 xi's minus mu k squared over sigma k squared. Plus log pi k minus log sigma k, and then I've got my indicator functions. Delta ci is equal to k. So there is this implication when I use this. I know what the x value is because I get to see it for the ith thing. I have that labeled in my code. I'll always know what the ith thing is. I haven't exactly written down that in the notation, but this is the part where you'll remember every step of this. I get to know all the information. I have all the x's in hand. Okay, so that's my log likelihood function. Now we're going to find q. So let's just follow the algorithm. We need to take an expectation. That expectation is over the length of thing, conditional on theta t. So theta t in our case is just all these model parameters that are floating around. So I'm going to condition them on my previous location. And so q theta given theta t is just going to be this expectation of the log likelihood. Keep in mind where the expectation operator runs. This is a linear equation right here. Expectations are linear operators, so they just slide over everything. And there's only one place that I have the c's. So what I'm taking the expectation over is the c's given theta t. And the c's only appear there. And so I'm just going to rewrite this and slide my expectation just through all of this, because all of this stuff is a constant with respect to c. And so this is just going to look like this. Double sum. I'll write it like this. I goes from 1 to n. K goes from 1 to 2. Just going to rewrite all of this. Xi minus uk squared sigma k squared plus log pi k minus log sigma k. And then I've got this same indicator function. Ci is equal to k. I'm going to do this in 2 steps. Just write down the second step. So normally I just take this expectation operator and take it over this whole thing. Where I've got my c's given all of my thetas. Once I take that all the way over, the expectation operator only modifies this part. So my expectation operator slides over all of this because there's no c's in there. C given theta t. So delta function that ci is equal to k. So again, what this notation is the xi data point came from component k, i.e. ci is equal to whatever that label is. So that's my expectation. Now I just need to solve this right here. Expectation of an indicator. So somebody help me out with that. What is the expectation of an indicator function? Say it again?
Probability.
It's probability. Yeah, exactly. And if you don't like that, think about a Bernoulli model. So what's the expectation of a Bernoulli? It's p. So Bernoullis are 1s and 0s. They have expectations. They're the probabilities of that one. 1 minus p is the probability of the 0. So this is the probability. Expectation of ci is equal to K. This is over my C's given this right here. If you don't like that I've got all of my C's right here, but for each one of these, it's an indicator function, I'm only dealing with one of them at a time. And so I don't need to think about all the other C's in there. All I need to think about is one of them. And so if you'd like, I can write down just CI right there. So I'm taking the expectation over that CI. The other C's aren't in there. I want to also remind you in this, we've suppressed a lot of our notation. I get to see all of the data. So I also have all of the X's in here as well. So that's that histogram of all of my X's. So I get to know in some step what I think my current information on the thetas are. My thetas are just the mu's, the pi's, in the sigma. So I'm just going to write down this thing. This is going to be in my current state of knowledge of the parameters is mu1t. This is mu2t. This is sigma 2t. And this is sigma 1t. And so it's saying that I've got in my mind some multimodal distribution, k-component mixture model. I don't know exactly that these are the right values, and in fact I could probably tell you with certainty they are not, but as this algorithm is running, they're getting closer and closer. So at this step of the algorithm, I have some idea of what they are, and I'm going to condition on that. That's what this notation means, right here. I also get all of the x's, but if I'm given all of the mu's, I also have some information about the pi's, because I have height in here. And so the heights are relative to that. They're not exactly the heights are exactly relative. The area under the curve is relative, which is a little bit different. So let's just think about this. If I have xi, let's say right there, given these parameters, this state of knowledge, I can probably compute some probability for this. What do you think the probability is that xi came from component 1? Just a quick guess. I know my picture is probably slightly not accurate. But what do you think?
65%.
It's at least over 50, right? So I don't know what it is, 65, 70, somewhere in, I would say between 65 and 85 sound like reasonable answers to me. But you get the idea, you can compute this probability, and we need to do that. I don't need to know where all the other x's are. That's the whole point. The other x's aren't helping me if I think I know the model parameters. Keep in mind what all of the x's are doing is they're estimating all those model parameters for us. Given the model parameters, the other x's aren't helping me directly. So that's conditional independence. So just think about what this is. Conditional on theta, I don't need to see all those, and all I need to see is just xi right here, if I knew this. So I'll write this down again as c, and just say all we're really doing is computing the expectation over that ci. So all things you just need to think about when you're writing down this notation. What does it all mean? What do I have? What part of the problem do I have? In this step of the problem, I'm assuming I know what the thetas are. So this is just a probability. That ci is equal to k given all of my model parameters. And I get to know xi. I could write down all the x's. They just don't have any information. So how much information is there about the CI? It's all in the model parameters and in xi. So if I did give you the model parameters with certainty, you could do this calculation. Question is how do you get this thing? So how do you compute? So I'll just remind you, we know f f of xi given ci is equal to k, and my model parameters, mu1, or I'll say mu k sigma k. And I know these for k goes from 1 to cap k. In our case, cap k is 2. So I know that. I want that. This is a continuous distribution over the x's. It's normal. And so how do I flip this thing around? They're very similar. These are my thetas right here. I will need to know all thetas to do this calculation. But here are my thetas. Here's my c. And I want to do an inversion to this probability. Here's my point about Bayes. There's only one way to do this, it's Bayes. So if I felt like antagonizing somebody that was a non-Bayesian, I would just pick on them for this. You're doing Bayes. What's the point, right? Okay. So this is going to come from Bayes' theorem. So what I'm going to do is I'm going to write down f of xi given my ci is equal to k, my model parameters, mu k, sigma k, and I need to compute right here probability that ci is equal to k. And I need to normalize this. For our example. That's Bayes' theorem. So the question is, what are these? I know what these are. These are just Gaussians right here. So these things right here, that's just 1 over root 2 pi sigma k e to the minus 1/2 xi minus mu k squared over sigma k. So the little f's are things that I know. This is a Gaussian mixture. That's what's responsible for the x's. If I knew the labels, I would know which mu's to plug in right here. So at that form we know. What's this? This is how I think about it. When I start deriving something, I look at every step and I think, what is that? What do I get to know? So conditional on what? So what do I get to condition on? Everything in the previous iteration. So I'm going to say this thing right here. These, you can do a couple different things with this. And there is some debate over what's the correct thing to do about it. But that's my prior. So I can let my prior change or not change. There's all kinds of things I can do with priors. In terms of a maximization problem, it's not going to matter really what I do here. But I'm going to say this right here is going to be pi k t. So that's my iteration at the tth iteration. That was that thing that we had computed, and I wrote down right here, what's that MLE? So the previous step of the algorithm, I have all these little pies floating around. I can use them to compute these priors. So in terms of a maximization problem, that's an okay thing to do. I'm taking my previous location. If you think about this as a purely subjective Bayesian, your priors should not be changing. And so some people might use that to be the uniform prior. Or they might end up put some prior weights on here. So let's come back and talk about this step in the many different things you see people do. In terms of just maximizing something, this is probably the best thing you can do. This is a reinforcement learning step, and it drives into that maximum faster. In terms of the subjective Bayesian step, I've got this prior right here. I dipped into my data to estimate it, I violated my likelihood principle. Whether or not I care about that, that's up to you guys. You can tell me whether or not I care about it all. So I don't, actually. So let's come back, look at this. We'll write down exactly what our likelihood function is. We computed this probability right here. The probability is in terms of all of the pi I k's, but they also involve this pi k up here is this Bayesian collider. So that's my total probability of everything. I know it from the last step. I should probably use it. We'll plug that in, and then we just need to optimize over the pi k's, the sigma k's, and the mu k's, and then we'll look at your EM homework. Tomorrow I'll do a review session if you have a question on the homework or anything else. So I'll be there at 5:30, same place as always. Thanks, you guys.